Hey y'all, I think my last video cut off, so this is going to be part 2. All right, so we are looking at a goal reaction. How can we use Hess's law to actually figure out this process? So I'm going to start by writing my goal statement right here. This is what we want to end up with in that whole summation. This is what we want to end up with, and then we're going to use that math to calculate that enthalpy of that reaction. Okay, so what I like to do though is write out what I know and make sure I follow. I start with the very first reactant on the reactant side, and I need that to be on the reactant side. So the problem is this is carbon monoxide. It's not an element from a formation reaction. So let me write how I would find carbon monoxide on the table. It's going to be a formation reaction, isn't it? Yeah. So I'm going to put a half here so I can keep that as CO. Okay, so this is going to be on the formation reaction, and I'm going to go ahead and give it that number. Okay, on the table, that is, I have written down 110.5. Okay. All right, now as is, that doesn't help me because this needs to be on the reactant side. So what can we do to this reaction to make this work? We have to flip it. And in order to flip it, this has to be positive. I'm going to flip that sign, and now watch this. I'm going to turn right around and write that reaction backwards. So I have CO, gas, and it is coming from carbon and oxygen. I love it. Don't forget to flip your sign. Okay. All right, so now what's next? I have NO, and it is on my reactant side. So I have to put NO here. Now, how would I find that as a formation reaction? Well, that is going to be nitrogen plus oxygen. And I only need halves of those. Okay, so what do I read from the table here? Well, I read that from the table as a positive 90.29 kilojoules, except didn't I flip that one as well? So let's go ahead and make that a negative. Okay, I love it. Okay, so now I've actually got everything present in my reactant side. And then let me just check. Okay, I've got this present, done. Okay, I already have the 1/2 nitrogen. Oh, but I don't have the carbon dioxide. So now we need to write another one, and it needs to have carbon dioxide on the product side. So how do we make carbon dioxide? Okay, CO2. I love it. Now let's read that from our table. That is minus 393.5. Okay, that stays. We didn't alter that at all, so keep that negative. We kept that going forward. And now we have our CO2 on our product side. Well, let's double check and see if we can cancel everything else. That's the first thing you do, is make sure you have all your species. And then the second thing you do is see if you need to cancel anything. Because remember, we want this overall goal statement, nothing extra. All right, our carbon is on both sides. Cancel. Oxygen is on both sides. Cancel. And look, what's left is we ended up with our carbon monoxide, nitrogen monoxide, nitrogen, and CO2. Now you can do the math, and let's see what you end up with. I calculated here. It is literally the sum, so plug that into your calculator, and I get minus 373.3 kilojoules for that overall reaction. Okay, I love it. You can always put in your formation reactions forward or backward from your thermochemistry table. All right, I see, I feel in my heart that you guys are asking for something just a little bit sassier. Let's do one more and let's go even a little bit sassier. So let's take an example from what we've already kind of learned and looked at. Okay, this is gonna be so much fun. All right, so let's take and let's look at a reaction, okay? And let's do that same process, except I think this is missing on your table. So a lot of times with Hess's law, you have to be given some data. You need an extra reaction or two. Now let's write out our goal. Let's follow our same process. I'm going to scroll up just a little bit. This is our goal. We want to calculate this one. So I'm going to go ahead and write all the way down here our goal. We're going to use ethylene. And that should be an F2. I think there's a typo there, okay? And then 2CF4 and 4HF. All right, that is our overall goal. Okay, let's follow our process. I'm going to start with that very first one. And I'm going to start with that ethylene gas, this one. Let's write a statement in there. Is that on our table? Sure, we actually used that in a previous question. So I'm going to go ahead and add that one in. All right, do we need to make that? No, we actually need to use that. That is on our reactant side. So let's write it as the backwards formation reaction. And if I'm using that backwards, if you check your table, it's 52.3 kilojoules. It's positive, so don't forget to flip your sign. Okay, I love it. All right, so now I need F2. Oh, hang on. It's actually right in there. So why don't we go ahead and add this one in. Carbon solid plus 2 F2s. CF4, and we left that as is, so I'm going to leave that sign as is. Okay, perfect. And then let's see, so now we've got the F2 and we've got the CF4. So what's missing? HF. All right, we need HF on the product side, so let's make HF. And let's make it in a formation reaction. So then on the table, we have, okay, on our table, perfect. All right, now let's see if we've got everything in place and let's see if we can cancel. Here's our ethylene, done. Here's our F2. Oh, hold on. We have 6 in our product, but only 3 in our statements. How are we going to fix that? Okay, well, we also need CF4, and we need 2 of them, and we need 4 of our HFs. So something's got to give here and here. So is it possible to multiply? Absolutely. Let's multiply this whole thing by 2. And then what do we have to do to our value? Times 2. Perfect. So there's really only 3 things you can do in Hess's law. You can use formation reactions from the table. You can flip your reaction and flip your sign. And then you can multiply the entire thing by whole numbers. So let's multiply this one down here times 2 as well. And now let's see if we're talking turkey. Let's start to cancel some things. All right, we have 2 carbons right here. 2 carbons. I love it. Now we have 6 F2s. Perfect. Here's 4. Here's 2. I love it. Our CF4, we have 2 of them. Okay, done. Let's see, our H2, oh look, 2H2, 2H2, we get to cancel. And then we are left with 4 HFs. I love it. All right, bust out your calculator. Let's do this math. And this is going to give me 2,486.3 kilojoules. So that overall reaction is going to be quite exothermic. Okay, so Hess's law, let's do a quick summary. Hess's law is incredibly valuable if you're trying to get to answers of something that doesn't directly happen in a formation reaction. This is really true to nature. Mother Nature doesn't follow always one step in every reaction. It can be a whole series of steps. You can also take advantage of being path independent and use several series of reactions in order to get an overall goal. So you could, in effect, not actually do this in the lab and use other reactions in order to get to that data. So this is how a lot of that thermochemistry table is filled in. While you might be able to do direct calorimetry for one set of reactions, you might not be able to use calorimetry for another set, but you can still get there using Hess's law. So let's say this reaction right here is actually unstable and really unsafe. Well, isn't it much better to take the series of safer reactions than it is to actually try and do an unsafe reaction and use calorimetry? There's all kinds of reasons to use Hess's law. That's just one of them. But I will typically word Hess's law questions. I will word it in the question, please use Hess's law. And I will sometimes give you extra data, and you can always use from the